Now we are streaming. La la la. Yo, what up, my homie G? Where'd you go? I'm not giving them back right now. Because before I can give them back, everybody has to have done it and I've had to mark it. However, the person who hadn't done it yet did it last night and I just got it. So right after this class, I will go on to ZipGrade and I will just release your marks. So you can at least see those and then I'll get it back to you. Okay? We want this reaction.
Reaction of B?
Why did you have it in?
You like to say 6? Do you like to really say that's very
Okay. We're going to do this reaction. I have to go get something hot. Put away food, please.
Luca, just eat it now.
Oh, then put it over there. We're not force feeding. It's all weird.
Oh,
That's not as bad as you think. Anyways, yeah, I don't hold my.
You're so happy.
But I have to use good words too. It was really good. I spent a lot of time on it. I don't know even gonna look at it.
also this reaction is not
Like,
there's like not enough time.
what I even know what the shades are. Like,
Where did the old food go? Also, where's the other? Oh, you do 2.
You need 2. I don't know if you need. Oh, it's 10:04. I'm sure.
So I'm trying to like
No.
Okay, what I thought was, the kettle wasn't actually going when I thought it was. So, this demo will take a few minutes for the water to heat up. I'm going to just plug it in over here. Please, nobody turn around and try to have a cuppa. There, now it's heating. Now we'll be able to do the demo as soon as that's done. So I am no longer going to do that. We will move on.
Can you go back?
What? Oh, yeah. Write down that reaction. That would be useful because then you won't have to do it later.
Well, Mr. Newfield, is that balanced?
We need 2 ounces.
Yeah, is it?
It doesn't look like it's balanced.
No, it wasn't these.
and 2 of them.
There we go. Yeah. Excellent. I was using this last day, right? TV, don't need to explain.
No.
Oh. Just switching from the projector to the TV. Everything else is the same because I hate sitting in the corner. That started when I started recording and I didn't have a wireless mic. And they took away my projector that you could write on because they brought in other cheaper ones. And then I found this TV sitting abandoned in the corner of the lab. Hardly anybody uses it. And it has pens. So now I'm unchained from the corner. I can do anything I want. I can like take off my shoes and just like teach things.
I'm doing that too.
So I'm like right here, and I can be here, and I can just like walk over here and like see what people are doing. I don't have to get up. No, I didn't break it. Oh, another thing you should be aware of, this whole time, there's been a camera in the room. I mean, I never turned it on, but just someone might have. It's now there. It used to be above the sound bar. I've moved it there. Because I'm moving around, the sound quality on there is not going to be very good, but that is made for a conference room. If one of you can check it out after this class, I've switched my sound to that one. because it might be able to pick up better, and we'll see if it's good. I've also asked IT to help me get a wireless mic. They won't buy it for me,
Are you live
Your mic
streaming?
isn't
but I'm
even
live
bad.
streaming right
Why
now.
don't we just
Yeah,
check
we
the
just
live
check it
stream?
right
Well, no, because we have to do class.
Mr. Nichols, his mic isn't even bad. Like on the stream, you can hear what people are like whispering.
Sometimes.
Sometimes, really?
Yeah, like I can hear Dylan and Sophia's conversation when I'm listening to it.
They are whispering.
Okay, we need to go back. Well, I'd be curious then, if anybody goes back, I'll go back later and investigate what that's
Speaking
like.
of Dylan, I guess favorite little guy here.
Hi, Mr. Dupo.
No way, bro. Stop to pick me.
Okay, let's stop. If you're late, I inspect your dress. Are you wearing a belt?
Oh.
You wearing proper shoes?
I don't pass that today. Do you want me to set the
No, see me at 6:30.
What a guy.
I can have
I will
we're
see you
gonna-
at 6:30.
your teacher and your house parent are gonna have a meeting with you.
Not wearing shoes.
They're the
You're
same
over
person.
there.
Thank
I
God.
don't need to wear shoes.
I'm
I
meeting.
feel like I would
Okay.
expect your
I'm
friends
eating.
to, like,
We've done that?
walking around with shoes on.
I'm
Chaos.
Wait, Mr. Dupo.
What?
I'm meeting?
Yeah,
My shoes off.
we're gonna talk about your dress. Ooh, okay.
How are you gonna inspect someone's dress while you're not wearing shoes?
Oh yeah.
I have my shoes.
Yeah, but
So if we have our shoes,
I couldn't.
So I
find
don't
You
my
could,
bag.
if you want to take off your shoes right now, you totally can. Okay. Okay, so come. I didn't realize that would cause this much chaos. What I would like you to do here
Feels good.
on this page is if we have a reaction, let's say we have the wall of chemistry, okay? Wall of chemistry, and I'm given a ton of ammo. We're going to start off as most reactions are written in a particular direction because that's tend to where you start. So you start with, you write reactants first because that's what you have, and then you're going to make some products. It might still go to equilibrium, but that's what you start off. So like our wall of chemistry, we start off with all the ammo on one side, and what's immediately going to happen? Zero. How fast is this reaction going? Very fast. So this one's going to go very fast this way. What concentration did this one start at? Zero. So what's its rate? Zero. So now this is going really fast and it's throwing it over, what's going to happen to this rate? It's going to increase fast because it's going to be going over. And what's going to happen to this rate as it gets less? It's going to slow down. And eventually they're going to be doing this. And then what will the rates be? Equal. Excellent. I would like you to draw that with the correct curve on that graph. What would the curve look like, and what would the graph look like? I'm going to color code it into green and blue. What would the rates look like? How's their water doing?
Wait,
Still boiling. Yes?
Wait, if I take off my shoes, would it technically be proper uniform now?
No, you still have the wrong shoes.
Wait, what's gonna happen today?
Oh, we're going to go over your dress, and you're going to have to show me your shoes and show me your belt.
What? And then what's gonna happen after that?
Privet House is a line pit for a reason.
A line pit?
Line pit.
Wait, so I'm just gonna get eaten.
Line pits don't eat you.
What's a line pit?
It stops the bodies from smelling.
So you're gonna shower?
Wait,
It's a lion pit.
oh, so you're just lying?
Oh, you thought I said lion?
Yeah.
No, I'm a chemist. Lime.
Oh, I heard
Yeah.
lion.
Yeah,
And
yeah.
I was like, why are you gonna throw me in a pit of lions?
because you were so
I don't have that.
Draw that. Where will the forward? Oh, I may have put that in the wrong spot. Where will the forward rates and reverse rates start? So where would we start with the forward rate?
Bottom.
Top, bottom.
Top, no, top.
Hands up for top. Hands up for bottom. Top's winning. Everything's done by voting nowadays. Forget truth. Where does the reverse rate start?
Bottom.
Bottom. Now draw the curve. What should that look like?
And actuation.
Dylan, you've come in late. You gotta get caught up.
I can try to answer.
Sipping your drinkity.
What? Am I not? Do I not have the right package? Oh no.
Now, what did we say? It would immediately happen to the forward rate as it threw some over. It would decrease. So we should see it going down. What should we see the reverse rate do? Go up. Now, will this be linear, or will it keep going down at the same speed?
It'll slow down.
It'll slow down, because this is going to start throwing some back. And so what you should end up seeing is you get a curve where it goes up, and then it starts to slow down.
And then they're both the same.
You get a curve where it goes up, and then they're both the same.
Like, it's the same or asymptotic? Or?
The same. Because once, whatever we're at, remember when we did it and there was fewer people on that side and more people on that side, but eventually, the side that had fewer people just got all the ammo, and you could only throw back as many as they threw over. The rate eventually becomes identical. So the rate, what's blue and green in color theory? No, not in binder theory. Color theory.
Binder theory?
What do you mean?
What is green and purple?
What are you talking about?
When they mix.
Well,
It's yellow.
hey Siri,
Purple, right?
Yellow.
It's yellow.
what color is blue and green mixed together?
Blue and red is
Brown.
purple.
It's cyan.
It's not.
It's
Cyan.
Siri has never
Siri is
failed
Oh,
me.
yeah, no, green and, yeah.
What's cyan? What is that?
It's like a turquoise.
It's teal.
Teal, green.
Yeah.
Oh.
I'm gonna go with that.
That's close enough. But that's blue. That's more of a turquoise.
Tell us in the supermarket.
That's
Again,
not
cyan, turquoise, these are all not real colors anyway.
It just asked us about color.
Yeah, I know. Okay. Nick. Dylan. So, their rates will drop. It will be because this one's going super fast at the beginning. It throws some.
You let your intrusive thoughts on.
What is happening? Yeah.
We copy that down.
That's touchscreen?
It's a touch screen.
I didn't realize that.
No,
That's the
neither did
first time I
I.
noticed
It's a
that.
touch screen with 5 fingers.
Why do you need a-
Hold it. Can I do 10 fingers?
Oh my god.
Oh my god.
Can we try 11 fingers? Like finger painting.
We should try, everyone pass the class.
Yeah.
It works.
It works.
All about 12 fingers.
No, the students, this is very distracting. I need to stop.
Keep doing it.
No.
One more time. One more time to copy the entire screen.
Now, so you start off fast, throw some to the other side. Immediately the other side's going to start throwing some back. So, but it doesn't have as much as it had, so it immediately drops. That one starts to speed up, but this rate's still going faster, so it's throwing it a ton of ammo. So this one is getting more and more ammo, so it's getting faster and faster and faster. And eventually they'll meet. It doesn't have to meet in a spot that's like even between where they started. It could meet down here. It could meet up there. It could meet at any particular point. It depends how, like if we took our side and I took one side and I broke all their arms. And then they had to throw it over with their mouth. It'd be a really low rate, but there would still be one and it would be identical. Yes?
With this new computer, when you stand there, we can't.
Oh, you can't see, right. You might, the other class told me you might have to move back one. But I will also try to move. Let's see how it goes. Did that boil? Oh, excellent.
Oil.
Perfect.
You guys see?
Well, you're obviously not going to see when I'm just moving something, but I shouldn't just stand in front of it either.
Yeah, that's
Okay.
what we were asking.
Yeah, when I'm just standing there explaining something, that's the other problem. Okay, I've got hot water
And cold water.
and cold water. And this is the difference between a static and a dynamic equilibrium. I'm also going to show you that in sort of like a physical demo, so get ready to move.
You want this? They don't mix it.
If you didn't know,
How are you going to pick it up?
hot water and cold water actually make a different sound when you pour it.
Really?
Yeah, you can tell the difference.
Oh, hot water is more like.
Yeah, got a little bit of a, I think it's a higher pitch.
Other sounds
Mr.
like
Neufeld, I
tea.
have an objection.
Well, that's
You're not
because
wearing
tea is
hot goggles.
hot.
That sounds like making tea.
Now, the other thing,
Oh, shoot.
If you were to like explain.
Should we come on closer?
no, one second, you'll see. I also, I am now switching the camera on. So,
Hi. Oh, wait.
hi.
Wait, is it only us or the screen?
Dylan, what does the camera do?
Oh my gosh.
Wait, why can't it literally can't say? I love this. That's totally fine.
This may be a dumb idea, but if someone's not here, they'll see the same, at least they might see the demo. Okay, this is that reaction I showed you before, NO2 and N2O4. The camera just saw it because it was in a beaker, but there we go. And then we're going to put one in here. And what I would like you to write down, is which one gets dark and which one gets light. The hot water or the cold water? Write it down. Just on the same page with the reaction, just a little note. Already, what can we tell? Hot, dark. The other one light. If you're ever in my grade 10 or grade 11 class and I came out and I said this is bromine, I just tape over the sign and I lie because bromine's a brown gas and grade 10s never know the difference. Sometimes I take test tubes and I just put a wrapping around the top and then I go, this is oxygen and this is nitrogen because it all looks clear.
Wait, so you lied to them?
Grade 12s wouldn't know either.
It's educational. It's not really lying.
Oh.
It's using a metaphor.
Can we have actual bromine in the lab?
Wait, what's in that too?
Bromine gas.
So this is that reaction. This is N2O4 and NO2.
Is it?
Yeah. But both of these contain the exact same gas.
Break it so I can
I'm
test
not
it.
going to break it. This is also what's in smog. So when you have nitrogen impurities in your fuel and you burn that fuel, in a hot summer's day, you see brown smog. And then people are like, oh, it's not as polluted in the wintertime. Yeah, it is. You just can't see it because it goes lighter in cold. So if I switch these to show you it's actually in equilibrium. So I didn't do it's not set this way. If I switch,
This is actually just small.
look how fast that's darkening.
What the heck?
So what's the equilibrium?
NO2 and N2O4. So one of those species is light and one of those species is dark. And I'm going to get you, based on the reaction, to figure it out because there's an energy term in there. And that would actually help. Now already this bottom part you can see is a little lighter than the top part just because that was in the cold. I'm going to go like that. Ooh, almost cracked it there.
What happens if you cracked it? What would you do?
A slight bit of smog would come into the classroom and I'd lose my demo. Like
You wouldn't like evacuate the class?
basically it'd be like we were living in Abbotsford.
Damn. Well, Abbotsford brothers.
No, Abbotsford has the most pollution in all of the whole Vancouverish area because all of the smog from Vancouver, the wind from the ocean blows it straight into Abbotsford. They have the worst air quality. You're surrounded by trees and smog.
Abbotsford.
Yeah.
I'm an L.
I grew up in Abbotsford until about grade 2. So I feel I have the right to insult it a little bit. I don't think we actually need to flip that one around. That's going. And then, of course, you can keep doing it. Whoa.
We need to do this for the rest of the class.
Yeah.
I just want to watch the colors change.
Yeah. And you can actually, can you see it pumping up the gas? Come, everybody, come.
Oh yeah, you can see it moving.
Yeah, and I'm going to put this one in just a second so everybody can see that. So everybody get around where you can see. Okay. And now we'll do it to this one. See this one? Okay, and what's smokiness?
Dylan.
Okay, well, your head's in the way, so nobody else can see. There you go, go like that. So you can see, like, the gas is just pouring out. So this is like the equivalent, we gave one side an advantage in our chemistry wall of science. And so that is just pumping out ammo. And when we go back to the reaction, we'll work out why that was a little bit. And we also know it's an equilibrium because it can go back and forth. If we change the conditions, it will settle at a new equilibrium. So changing the temperature changes the equilibrium. But if we keep the temperature constant, it goes to a constant color. Have you seen anything? Let the shorter people through. Okay, if you have seen it, if you can go sit down and let people who haven't seen it. No, but can you see how fast it's changing?
Oh, yeah.
Yeah, that's what I wanted you to see. All of that. Yeah.
How fast? What is? I'm just eating before.
You know that you're being recorded right now, right?
What am I?
Do you see it? Just that?
Wait.
Do you see how fast it's changing? Like when I put that in there, you can see the gas just getting pumped up. Yeah. So that's what I wanted you to see. Is that good?
How does it go that quick?
Can you put it back in here? Why
And then-
are these the same?
Yeah, they're identical.
The gases.
The gases are identical. They're a mixture
How do you
of.
get them in these things?
Oh, you can buy them from a lab. They have ways of. I didn't do it. Chemistry laboratory company.
Wait,
did.
do they break this and then like melt it together?
Yeah. They put it in there and they just melt it together, and then you've got a sealed thing of gas.
That's cool.
Yeah.
Is it poisonous gas?
Yeah, it's smoke. It's not good for you.
Oh,
Don't break it.
I won't.
Crazy person.
Why do you so much more chaotic?
Okay. And I was chained in the corner. I am now unchained. I am unchained.
There's no snack boxes in there. Lunch box.
Where?
Lunch box, not snack box. Extra box.
Why is everybody yelling about boxes? Turn around. Get chemistry up. What are you complaining about?
Switzerland's snack.
Apparently, a snack box and a lunch box are different.
Yeah.
Okay, I'm not going to talk about that. Okay. If we put it in hot water, what color? Yeah, focus. When we put it in hot water, what color does it turn?
Brown.
Brown. First of all, is this an endo or exothermic reaction? Endo. So we know it's an endothermic.
Well, depends from what side.
And well, we always look at it in the forward direction. Unless they specifically say reverse, always assume forward direction. We write them that way for a reason. And if it was cold, I wrote cold in red. That's going to be very confusing. And hot in blue. No, let's just be consistent. Cold, what color?
Brown.
Well, it got lighter, right? So to give it away, this one is completely clear. You get cold enough, you can get it almost perfectly clear. The smog is still there, it's just a different form. Now, it will form an equilibrium at a particular temperature. Now that these are just sitting here, they're not really changing. They're just at that temperature, and now they're going to stay that way. And so it'll stay that brown, summertime, stay that particular light brown, because it's an equilibrium. This is a weird arrow, it's going both ways. Twice the chance of a date on Saturday night. So, the question is, which one of those molecules, is this brown? Is that one brown? Is this one clear? Is that one clear?
The one with energy is brown.
Why?
Because that's hot, which is energy.
Right. This side needs energy. Does this side need energy? No, it releases energy. So if you give it energy, this side has an advantage. Its rate increases faster than the other. What happens when you increase the temperature to a rate?
More kinetic energy.
Increases the number of collisions, particles move faster. So the rate increases for both. So if we were to look at the rate for both would jump. So that would be, say, one rate, this would be the other rate. But they won't increase the same amount. This one requires energy, so it gets the most benefit from increasing the temperature. So it turns out that since this one requires that, then of course, if this one has an advantage to getting energy, where's all the ammo going to go? Sorry. Which side?
To the right side.
Don't say right and left, say product or reactant.
Product.
Product. So it turns out that this side, do I have a brown? Sure. Maybe orange.
It's pink.
Brown.
Never mind.
This side is the brown side. Because this side, if this one gets an advantage and it rates, if once the side whose arms weren't broken, where did all the ammo end up?
On the other side.
On the other side. So the stuff ends up on the side that's the weakest.
What is this stuff?
N2O4 and NO2 in this case. Like, this is just chucking itself back and forth. Yes?
Wait, so when there's an equilibrium, it means there's like an equal amount of stuff on each side?
No.
Oh,
Because, are these both at equilibrium now?
no. Well, yes.
Now they are, at different temperatures. Do they have the same amount of each one? No, which one has more NO2?
The brown one.
The brown one, because we changed its equilibrium at different temperature. If we keep raising the temperature, it will change, and then it will become consistent at a temperature. So they are not equal. In fact, you could have 99% here and 1% there, but it's still going.
Could it ever be 100% at 0?
We call that going to completion. So that means the reaction just went.
Oh, so equilibrium is basically figuring out how much is on each side.
Yeah. Now,
Okay.
I don't know how to write clear in clear, so I'm going to write it in
White.
light blue. Because ice always seems clear, but it's really blue.
Really?
Yeah. Yes?
Why isn't the reactant the brown one? Because it has the energy, so it's hot.
Right. So you give so this is the reaction mechanism, right? Not the reaction mechanism. This is the energy reaction. It's an endothermic reaction.
Yeah.
So it's going to go like, nope, Mr. Neufeld, what are you doing? And it's going to go like, so this one needs a ton of energy to throw it to the other side. This side needs very little. And so they're going back and forth. And at room temperature, they were whatever color I brought them out. They're sort of a light brown. That's the temperature. But if I give them energy, this one already had a lot of its molecules having enough energy. So it was throwing it to the other side. It was clearer. But as soon as I increase the energy, now this side has energy. It can throw more molecules that side. It helps this side more because it's further down. It needs the energy. And so it's going to utilize its reaction rate increases faster than this reaction rate increases. Because this, since it requires so much energy, it just makes more of a difference. If you give a person $1 million, $100, probably doesn't make a very much difference. If you give someone $100 who only has $50 in the bank account, it might make a huge difference. Now they can go and get that job because they can afford the taxi and the haircut and everything else. So when you have less energy, sorry, let me make sure I phrase this right. Not when you have less energy. When you require more potential energy to get over the hump, then increasing in temperature will shove it the other way more. Another way to think of it, and we do this later, so I'm getting a little advanced here because I'm not going to talk about it quite yet. But another way, what would happen to the equilibrium if I shoved a bunch of N2O4 in here, like just dropped it in? What would happen to this rate? It would speed up. And then what would happen to this rate? It would speed up, but it would speed up to match, and you get kind of a diagram we saw there. So you can think of this like a reactant. It's not just energy plus N2O4, but let's think of energy as like a thing, like A, and I dropped a bunch of A in. It shoves it this way, this gets more stuff, it starts shoving back and you get a new equilibrium, but more goes here and so it's brown. This is also a dynamic equilibrium. So, could everybody put all of this stuff into the bag and clear the desks? Yeah, thank you.
Putting your desk?
Put all your stuff away and get everything off your desk. Like, put everything in your bag.
Are we having a contest? Bag.
You're not allowed. I don't know how You're not allowed. Oh no, we're recording.
We're recording.
Mr. Nicole, this is a test.
But everything away, why would I be joking? It's so exciting.
Wait, did we get our old test now?
Did you drink
No,
too much
the next
coffee
day.
today?
Oh.
How much caffeine have you had?
Mrs. Newfrau. I'm a chemistry teacher.
It's shame to know it's
I had some blue crystals this morning that I made last night. And they were sugar, just to be clear, for anybody watching.
Can we make
Yeah, I think I know what he's gonna do.
chemistry,
You know that?
and because I want to eat some sugar balls.
I found out you can, there's a lab you can do in grade 10, sorry, you're not gonna see it, where you can make cheese with like normal rennet and GMO rennet and see the differences. No, you're wrong class. You gotta come back to my grade 10 class. Yeah.
Wait,
Okay,
Can we make cheese and all?
next one, I would like you to take all your desks and chairs and just, we need a big area in the middle. You can actually put a row down the middle just to use up some of the desks. We're gonna get in a circle. So we need a big area, put some desks in the middle, just clear the area. Maybe put a double desk thing down the middle like this. I'm not gonna have you get jeans and do anything, but why don't we do this just to get rid of some of the desks? And then shove everything to the side, ready to get around.
Are we doing this? We're doing this last time? Wait, are we doing the figure
You can see how much the demo costs. Just like buy it.
Oh, yeah.
Actually, we should do it on there when we make food. Yeah. Anyway, let's go. Put everything away. Get chairs to the side. Get desks in the middle. Stop standing. Go find someone. Move a chair. Stop standing. Move something. Get a desk in there. Move that desk over. Let his desk come in afterwards. Excellent. Drawings. Yeah, bring those in. Perfect. Can we get that desk and that chair on the inside? Shove it all in. I don't know if this is. Oh, we're gonna get another one in there? Sure. Excellent. Are you looking?
Where does this read?
Okay. Get into a circle. Put away your. What's your phone doing that? Put your phone away. Okay. Gather in a circle around. Just get in a circle. Get in a circle. Like right around the table, all the way around. Okay, I'm gonna just say start walking in a clockwise direction.
Huh?
Start walking in a clockwise direction. No, you're around. You're around. You go. What are you doing? Get in a circle. Yeah. Yeah, we're walking and we're filming it. Remember the part of the lab where you said that you do anything I say, and I could say you could tap dance?
Don't make us tap dance.
Don't make it tap dance.
I'm
Now stop. You got past it. We're gonna go like this. You go forward. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Okay, keep going.
That's dripping musical chairs.
Stop. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Now, from an up, way high in the sky point of view, if you were just counting the number of people on each side, would there be any change? No. Because we're dealing with individual molecules, we might see 7, 8, 7, 8. But roughly, if we're doing thousands, you wouldn't see a difference. This is a dynamic equilibrium. You are moving. You individually are changing sides. But the entire system is not changing. This is like an equilibrium. Now I'm going to demonstrate a static equilibrium. Very carefully, don't move. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Okay, now careful. Don't move again. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Now, obviously it didn't change again. One of the first experiments they did to show that like dynamic equilibrium exists is that they took things that were identical, but they just made one side radioactive. So they took a saturated solution, and they had a saturated solution of iodine, and they put in a crystal of radioactive iodine. What does saturated mean? Nothing more can dissolve. And so when they put it in there, nothing more can dissolve. What they found is the radioactivity in the iodine, because it's a dynamic equilibrium, now you can keep walking again. Some of the iodine actually came off the crystal, and some of the iodine in the solution went on the crystal, even though the amounts didn't change.
And then he's saying let me write the text.
Does anybody have any questions about dynamic equilibrium?
Just stuff in my foot, buddy.
I'm probably standing in the way of this beautiful thing. Excellent, you can put all your desks back now, get all your chairs, get all your books.
You really
Well
did
done,
all of that.
excellent.
But just
All of
don't
that,
walk around
that's
in
all it
circles.
was.
Wait, let's go slowly. Slowly.
Don't, but quickly!
No.
Schnell!
How much more do you have today?
None?
Are you okay?
I've had none yet. I usually have my caffeine in the afternoon. But, Unchained.
He's probably gonna watch it.
And then you can get ready for your surprise quiz in equilibrium. People are just moving slow. I thought a rise in blood pressure would.
Yes. Look at your chair.
No, I actually want to know what's gonna happen. I can't hear this. I'll take that.
Today is Thursday, grade 2, 11:45. Oh, we got lots of time. Excellent.
Are we doing a fire drill?
No, we did that C block. We don't do it multiple times a day. You
What
want
was
to
our-
keep doing the fire
What was
drill?
our Eastern problem?
We have to do the earthquake drill today.
Yeah, my bad.
Our iodine level.
Your oh, that I just got. I have to check. There was maybe one person who hasn't had it in.
Why?
Dylan, is it in?
No, I didn't put them under the bed.
But it's getting there. It's very close.
Why don't you punish him for that?
You give him Saturday night
I do
I
all the
just was
time.
on Saturday night.
But you can't punish him any more than he already is.
Wait, what's my punishment?
Give him house jobs.
Mr. Neufeld, but what
What's
was the
gonna be my-
average for
Pardon?
every, like, other than Dylan, what was the average?
I don't have an answer.
level 3.
Oh.
I marked your tests. They were ready next day, but you're allowed to take a bit longer.
Wait, but why can't
I
you
wanna
release
know,
the
like,
marks
how-
now if
Well,
everyone's
we wanna
done
know if we
tests?
were better than the.
I am right after class. I said I would right after class.
Why that's not your game.
Because I only just got the test. I only just knew now that it was available. So I will right after class. And if you don't have your zip grade code, email me. And I actually managed to figure out. I downloaded like a whole bunch of sheets as separate sheets rather than one big file. And so I can just attach that to you and email it back to you, and then you have it forever. Okay. So equilibrium is dynamic. Equilibrium doesn't have to be at the same concentrations. Equilibrium will eventually have the same rate. There's now a bunch of fact things that we learned.
Why was there a quiz?
Don't tell Dylan. Part of his punishment.
There's a quiz today.
Once the quiz starts, Dylan, you're not allowed to talk.
You don't study for it?
Here we go.
Now it's the last class.
Look. Sophia, book out. Stuff ready to go. Rate of consumption of reactants equals to what of products? Sure. So we know the rates are the same at equilibrium. We did, now, one of the problems that every example I give you does show you equal amounts because when you walk around the table, everybody just naturally spaces out. Of course, products don't do that, and reactants don't do that. Their rate is more like when we were doing the wall of chemistry and like I took people from one side. There's a different amount. Since there's always going to be an energy term, one side is always going to be at an advantage or disadvantage in some way. The concentration of reactants then doesn't equal the concentration of products. And I have a note here because it's a bit of a lie. I put this in here because it's not that it doesn't equal, it's that it doesn't necessarily equal. It's not this is something that people just see equilibrium and they go, oh, it's the same on both sides. It's not. It's an unfair system.
Concentration of which better.
So it could be equal, but it could be equal in the same way it could be anything else. Probably unlock that door. Everybody who goes gets locked out. I mean, I was locking out Dylan, but he managed to get it inside, so.
Wait.
And now my key's caught in my keys. Never mind. If they're not equal to each other, what can we say about the concentrations at equilibrium?
Almost equal.
No, they could be anything. Some equilibriums have like a tiny percent on one side and some on the other. Taylor.
Oh. They're
At equilibrium.
They are at equilibrium. What can we say about the concentration of the two gases in this tube?
well,
They have the same amount.
They're the same.
In a
They're not equal, but each one is unchanging. They are constant. Sorry, I have to slow down because my writing, I don't know if it gets worse or better, but sometimes I lift the pen up and it still does it?
I mean, it's the same as you're writing on iPad.
Yeah. Sure. What? Oh, sorry. You should get you a buzzer.
Like a lip, yeah, that's what I
Yeah.
just.
Forward and reverse reaction rates. Now, this one's so important, I apparently said it twice, because the rate is consumption of reactants is the rate of creation of products. Forward and reverse reaction rates are constant and equal, yeah. I wonder where I could put this, because if this was gone, I'd probably stand over on this side more often too. I could switch. No, figure out where to rearrange the classroom. At the end of this year, I get a whole new classroom, so.
Wait, what?
The new building.
New
Wait, are we
building.
gonna be in the new building whatsoever?
What grade are you?
No,
Well,
Patel
what-
did open that next year. No, Patel said that he's gonna get all the grads to walk through it first.
We're gonna walk through it. That doesn't mean we're having classes.
We have like a week of class.
Dylan, chemistry. Excellent, thank you. A system not at equilibrium tends to move towards a position of equilibrium.
You're writing on a position that.
What are we supposed to write down?
You'll see as soon as I move.
Equilibrium.
I have to, this is now like old school when I did it in front of a whiteboard.
I prefer this.
I actually have to have time to write it, you have time to write it down, I have to move it away. It is a little bit more chaotic. I can just walk around and see what people are
I
writing down.
don't think it's more chaotic because you're kind
No, I like this a lot better.
If I had a laser pointer, I could write from here.
That would be awesome.
It'll be so much
Really bad.
because we could read that.
I feel like it's gonna be
Yeah,
so
that
messy.
writing
Yeah,
would just
I
be
think we could
scribbled.
probably do
Yeah.
Yeah, maybe.
Already,
Maybe.
you can barely
I think I'm
do
good.
it.
Now, the reason, and this is a fundamental force of nature. It always amazes me when I see an equilibrium, and I think having a deep understanding of chemistry and equilibrium really helps out in any area. If you make a change in the universe, there are forces that will work to undo that change. For every action, there's an equal and opposite reaction. But in addition, remember, this is hot, so it has this particular equilibrium. I put it in there, and of course it's shifting to the other side, it's going to get cool. But because that is an endothermic reaction, we're cooling down, what is happening to the energy as it's getting clearer?
It's getting,
Going.
it's going down. No.
It's going into the model.
It's going this way. I've decreased the energy, it needs more energy, it's going this way. So energy is literally coming out of the reaction. And so because we're cooling it, it's trying to make this hotter. Because this is using up energy, it is actively also cooling it. When you make changes, it will also make, because it's absorbing the energy. This is why we get very little snow down here. We have all that water, sitting out there. As soon as it cools down, the water tries to freeze. As soon as it freezes, that is an exothermic process. It releases heat into the environment, and then all of a sudden it doesn't get as cold. In the summertime, when you try to evaporate water, that is an endothermic process. All that heat gets sucked in. So that's why if you live around here, that whole equilibrium means that we have fairly mild temperatures. We have this big heat sink, essentially, outside of there that's doing something a little like this. Whereas you go into the interior, what's their summers and winters like?
Really extreme.
Yeah, they're awful. Why would anybody live there? Yes?
So basically what you did with those test tubes is you're like reversing and...
Yeah, but I'm not, both reactions are still happening. I'm just emphasizing one over the other.
Oh, I see.
So when I put it in hot water,
Oh, so like when it's
the
hot-
forward rate just ramped up. And then once we had a high enough concentration on this side, it can only shove it back so far, and so now the rates are equal, and you get a very
Oh, so you
brown
would
thing.
just put like, for the brown one, it would just be like the brown would be at 80% equivalent.
Yeah, so it might be 80 and 20. And if I put it in cold, it might be like 75 and 25, depending on the temperature.
Yeah.
Yeah.
Oh, I get it now. I get it.
Nice.
That makes sense.
Everybody, if you have questions, see Dylan.
What? Don't get it that much. I get it.
One of the most when you look at different study techniques, number one, the worst study technique is reading over your notes. You're not doing anything active. But one of the best ones is finding someone who knows less than you and explaining it to them. They have shown time and time again that the tutor learns more than the tutee. Or the tootle, depending on which English version you want.
I like the
The tootle. 6, macroscopic. So you've heard of microscopic. What does microscopic mean?
Big.
Small. What would macroscopic mean?
Big.
Big. So when we're looking at that, can we see the molecules changing?
Yeah.
We can?
You can't see the individual molecules.
You can't see the individual one. In fact, and because it's now at an equilibrium, when I showed it to you, you could see the equilibrium change. But now that it's at equilibrium, can you tell that this is a static versus a dynamic equilibrium? The macroscopic, the color doesn't change. That's a macroscopic. Stuff you can see, big stuff. Dylan?
Oh, sorry, no, I was just saying, what do you mean by at equilibrium?
So, macroscopic would be a large change. Color, size, mass, volume, etc. Big stuff. One of the things, you may have heard of this global phenomenon that some strange science people are worried about, called global warming or climate change. I think it's come up in the news a couple of times. And really the warming, I mean, people can move. It will just displace hundreds of millions of people and disproportionately affect people of lower socioeconomic status and all sorts of terrible things. But changing in that, survivable. Right now, with the rise of CO2 in the water, we are changing the equilibrium of the ocean because CO2 reacts with water to make carbonic acid. Carbonic acid then breaks down into H+, produce HCO3. So as the CO2 levels are rising, yes, the temperature is getting hotter. Who cares? It's also making our acidics our oceans more acidic. And at some point, the equilibrium will exceed that by which shelled creatures can maintain a shell. At that point, every single sea creature won't have a shell, and that ecosystem will completely collapse. If the ocean ecosystems collapse, it will start collapse of ecosystems on the land.
What? Why would it?
Even if this wasn't increasing in temperature, we desperately need to lower our CO2 level.
Will it hurt to go in the water?
No, it won't notice you. Just there won't be food anymore.
Yeah, but if it's
But
like
why
more
won't they be able to
acid.
have a show? I mean,
What is this?
Because
Okay, I don't like.
you have to.
the acid breaks all the shells.
Ocean biscuits.
The calcium carbonate that's in the shell dissolves in acid. So it exists in an equilibrium. This exists as an equilibrium. As we're increasing the amount of CO2, we're shoving the equilibrium one way, just like we shoved it the other way by changing the temperature. Also, temperature also affects this, and as it gets warmer, it also gets worse. And you may say, CaA, CO3, it's shells on creatures. I don't like seafood. Who cares? If an entire ecosystem collapses, there are animals that eat that, and there are animals that eat those animals, and there's land animals that remind that. Once a whole ecosystem collapses, we can't get that back, and it affects all the things we eat.
Oh, so it's like a chain reaction.
It's a chain reaction.
So because
So,
I didn't deacidify the ocean.
so we need to lower CO2. Now, that means,
Just dump bases.
number one,
Like
some-
dump like basic.
someone actually tried to do something very similar to that off the coast of British Columbia. They dumped a lot of iron in, which created a huge algal bloom, which then all died and went to the bottom of the ocean. It was a carbon sink. We don't know who did it. Someone did an illicit, illegal experiment. One of the problems if we start dumping chemicals in, we may induce other change. So for example, in one area they tried doing something like that. It did something to the seafloor bottom, which causes a release of a huge amount of methane because it killed something. And then all that methane goes in the atmosphere and it actually breaks down the ozone layer like that. And it also increased our temperature because methane is so much worse than CO2. And so, you got to be careful with planet-wide experiments.
To like fully mess
Really? If we converted all our electricity to nuclear power, we could probably have a real decent reduction fairly soon. We would have, it's choices. Are we going to put up with nuclear waste or are we going to put up with our creatures dying?
Okay, but like,
Yeah.
if we didn't do anything about it, how long would it take?
Oh, I have no idea. They're just really worried.
On the ground, don't worry about it.
Yeah.
Put it in a concrete.
We'll still have
At the end of the day, the more you can do to buy less stuff, the longer we have.
So coming to boarding school on like every year is really bad.
That might be bad. Find a local day student and just say, I'm sorry, I'm staying with you. It's the environment. And just move, don't even ask, just move in. Yeah.
Facts.
Actually, that's a really good point. You're making everybody go away. You're bad for the environment, Mr. Neufeld. Nothing takes place in a closed system. Can someone give me an example of a closed chemical system?
A container.
with the lid.
Give me an example of a container.
Like a Tupperware.
And sealed?
Yeah.
Yeah, that's a closed container.
With a lid.
Pardon?
Pot with a lid.
A pot with a lid. You don't want to prevent things from escaping. If you're doing something in a pressure cooker, that's a sealed container. The water can't get out. All the reactions stay inside. An equilibrium can't happen, Sophia, if the stuff is disappearing. Nicholas?
So it has to be in a closed system.
It has to be in a closed system. Because if you have a reaction, to go all the way back, imagine we go back to here, and they fire everything on this side, and there's some, like, a chemist on the other side who really wants this and keeps taking it away. What will happen?
There'll be no more survivors.
There'll be no more ammo, and then, so it will just go to completion. So if you take stuff away, it's an open system, you don't get an equilibrium, you get a one-way reaction. If you started taking away from this side, you could force the equilibrium to go that way. So you can play around with equilibrium. So, open system, reaction often goes to completion. And I'll step out of the way in a moment. There you go. Also, I'm going to put in changes are constant, dynamic, looks like static. Everything's shoving equilibrium around. I see equilibrium every single place I go. If you look at even human behavior, you put in different rules. You can just shove, you're always gonna get people doing everything, you can just shove the equilibrium around. How many are gonna do what, and what are you gonna do to affect that particular equilibrium? Okay. Good. Anybody still writing things down? I'm standing in your way. Nope, don't need that. Are we still? Yep, everything's still moving. Okay. What was this? I'm sorry. When we did the whole table and we were going around and you were like changing positions, I was supposed to play a song.
Oh, the times they are changing.
That's enough.
Is it just when you click concentration?
So like.
Yeah.
Wait.
Bob Dylan.
It's only a fraction of the song. It's not
Oh, how do you
Oh, the times they are
Dance.
Dance it.
I don't dance.
Dance. Where's your hair band?
Choose someone to do
Yeah,
it.
we're doing.
What does that have to do
You
with
have
me?
to-
I'm not doing that,
Is
man.
it not when you click the other
You
words?
have to
Is it
do
just when you click
The whole science department, let's put on an air band or a band and we're all gonna get together. I'm like, delete that email.
Wait,
You
is
guys
it just
shut
when you
up.
click is it when you click other words? Or is it just concentration?
Oh.
How do you do that?
It's actually just, it's magic.
You just basically
Yeah, it's
set a
magic
play
and
button
magic.
so that whenever he clicks it,
Yeah.
it plays.
You're-
Remember-
That's back now.
It's just an input box.
This-
Just a button box.
This is not a whiteboard, it's a magical computery whiteboard, which can do stuff.
It's a smart.
It's a smart board.
No, literally.
Technically, it's not, it's a smart board program. They actually sell smart boards, we don't have them. Yep. No, stop that.
What?
That's one. I addressed it at the beginning, and you're asking me in the middle of my lecture.
No, you said you'd give it back at the end of that.
No, I didn't.
What?
No. Eshwan, see me after class, we'll talk
You
about
said
your
he was
listening
gonna
skills.
post
Okay.
the
If something is at equilibrium, right now, this is at equilibrium, what's gonna happen?
It's gonna stay.
The
It'll stay
rates
there.
are equal.
It's gonna remain constant.
So, like, with the happy faces, right now, what's gonna happen?
They're just gonna.
They're gonna shoot them.
They're gonna shoot. So, these four are gonna come over here, and that one's gonna go there, 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 and that one's gonna go there. So, a lot of action happened, but if you were just to count at the beginning and the end, did anything happen? No, so that's why it's an equilibrium, that's why we wired it around the table, that's why I show you those. You can't see the change unless you change the environment and you change the equilibrium itself. If it's at an equilibrium, static, equilibrium.
Oh, that's so cool. That's so cool. How do you do that?
I do it like this.
Make it bounce like 5 times.
I can't,
Do it really fast.
it has
What if
built-in
you-
friction I can't change.
What if
If
you-
I could lower it and make it go bum, 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 I would.
What if you make it hit the other side of the screen?
Like this side? Like, throw it.
Yeah.
Huh?
I
Yeah,
feel like
yeah.
it's like bounce off again.
Yeah. But I think we got the point.
Try up and down.
Oh.
In terms of where we at for our spreadsheet, I don't know if I've updated where we are, but we should be able to do questions 1 to 13. The graphs are really good. Now, this is not the Excel spreadsheet that tells you exactly what to do. So there are the minimum questions. Do more as you need to if you need more practice. And now we're going to do, so I'm introducing those because we're going to do all 3 of these at the same time in the last 5 minutes. Because I'm going to introduce a new topic. Should I play the video now or next day?
No.
No? No, I'm going to play the video next day to reintroduce it and remind you. Okay. Why do you have little cards up?
Oh, I'm writing stuff down.
What binder do you have up? Are you studying for another class in my class?
No, that's our plan.
It's your
Writing
daily
Oh, okay.
schedule.
That's fine. One student did once get bonus points for filming themselves studying chemistry in their English lit class. So, you know.
But you don't
Wait.
give us extra credits for studying.
Wait, you
for
get-
other classes
wait.
in this.
No. I told their English teachers so they could lower their LSAs in that class. Because everything, again, is in equilibrium.
But Mr.
It's a
Newfeld, do I
horrible
get extra marks
grade.
because Miss Hedquist got mad at me for doing the lab inside her English class?
Right. So, yeah, you should always be working on my class and my class, and my class in all other classes.
That's what I was doing.
Yeah, excellent.
Yeah,
Yeah.
but you
But I
don't
can't
send
save you from Miss
videos,
Hedquist.
there's no-
Miss Hedquist scares me, so, you know.
She really scared me and then I never did it again.
So we know what enthalpy is. We're going to probably redefine it in just a second. We've seen that with energy, but we haven't talked about entropy. So I've told you before, there are two fundamental forces of the universe. These are both of them. There's energy and there's randomness. We don't know really why.
What about vibes?
They are particular. Vibes are energy. That's why you say somebody has bad energy. They move towards a position. And these phrases are the magic phrases that you're going to need to pay attention to of minimum enthalpy and maximum randomness or entropy. And we're going to predict the results that happen when both favor the products, both favor the reactants, and when they oppose one another. If they oppose, what do you think we get? There's a force thing going this way and a force thing going this way.
Reaction.
You get
What kind of reaction? You get an equilibrium. If they're both going towards products, what kind of reaction do you get?
a product.
Yeah, you got, well, if they're both going to products, do you get an equilibrium?
No.
No, then you just get a plain old-fashioned grade 10 reaction. It goes all the way. If they both go to the reactants, what do you get?
A reverse reaction.
But if you start off with the reactants, nothing happens. It just doesn't go. Or you put in a ton of energy to force it to go. Because if they both oppose it, that reaction is just not going to
What would
happen.
an example reaction be for that?
Doesn't make any point.
There's no example reaction because by definition, those are things that don't react. So like helium gas and lead never react. You never get helium, lead, helium, halide. That's a weird thing to say. Because they just don't react. It all opposes the other way.
Force it to react.
They literally won't react. If you can make a noble gas react with something, there's literally a Nobel Prize in it.
Oh.
In fact,
Take one.
a team at UBC managed to make a compound with xenon, which is a really big noble gas, by trapping it in a chemical cage and showing there's some faint interactions on the outer electrons that were technically bonds. And they literally won a Nobel Prize for
You get $1
doing
million
that.
for
But
it.
the lighter ones, we don't think it can happen. If you can make it happen, you've shown us something new.
You
That's
get
the
$1
whole
million
point.
if you do that?
You get the Nobel Prize, which I think is like a gold thing, and I think there's a cash like $1 million.
How much could you sell the gold prize for on eBay?
Fair bit. Quite sad that a lot of people who have won Nobel Prizes have actually sold their Nobel Prizes because they don't get paid a lot to do their work, and then they live somewhere without health care like Canada has, and then they have to sell it to pay their medical bills when they're older.
Sick.
That's just happened to somebody. Someone saw it up for sale, bought it, and then gave it back to them and also paid them extra money for the medical bills because right now, in certain countries of the world, raising money is the only way to get health care. Okay, enthalpy. We already know this one. What is the symbol for enthalpy? Delta H. And what does the H stand for? Heat. So this is the heat the delta stands for change, the H stands for heat. The heat content of the system.
That was the energy content.
Heat is energy.
You're gonna write.
So, no, you can write heat. The reason being is I don't want you to confuse this, so it literally stands for heat. And if you have an exothermic reaction, what comes out? Heat. And if you have an endothermic reaction, what do you have to put in? Heat. So delta H is heat. So It is.
Yeah.
We're,
But wait, like, what if you like light magnesium?
light comes out, hits a wall, and what does it turn into?
Heat.
Heat. Sound comes out because it makes a bang, hits a wall, the wall vibrates. What does that turn into? Heat. The fundamental force, everything eventually will turn into heat. The sun will die, it will expand to a red giant and come to see Earth's orbit. It will then eventually cool, because I don't think our sun's going to go supernova, become a white dwarf, red giant, white dwarf, black dwarf, cool off, and then be an empty, cold place for the rest of eternity.
Then will it eventually just disappear?
Well, gravity might take it all back together again in billions of years to make a new solar system out of all the stuff from all this area. But eventually, that's going to stop happening too. As everything gets used up.
No, eventually the universe will die because it ends up coming up.
Yeah, that's entropy.
That's entropy?
Yes.
That's terrifying.
Wait, can you post the quizzes?
People just said eventually nothing in the universe will exist because all energy in the universe.
Yeah, and eventually, like one day, you'll die. Same concept.
Okay, yeah.
Like by the time that happens, you'll be dead anyway. So like,
So at least we did the
Hey, no, I mean, are you trusting it in the it's gonna like be after getting like that's not what?
Did this happen in SEC?
Yeah, that's what I
So Mr. Sullivan was there? And he told you I will talk to the officer. No, I think that makes sense.
I literally get like at the first slide. I don't understand why.
He said 115.
Like,
Check your email. What? Check your email. Mr.
like the
Yuval.
first slide that we
Right.
took.
So this is B,
Yeah,
this is
and that one's
A,
good.
and this one is,
Wait, no, it was the one where it's like the gas was clear.
yeah,
Oh yeah.
yeah, so that was,
Yeah, at like the very start.
Thank you.
Like the very
Oh.
first thing you did today.
Luca,
Wait,
if you could stick around for a second.
oh,
The very first thing you did.
Don't hit anything. So let's go that one. Because I was just using A and B, but they're both an endothermic reaction. So A,
Yeah.
B, brown.
Because to me, it's like if the energy
Clear.
is here, then it's moving a lot, then it's hot,
So
then it would be brown.
the energy's here, it's moving a lot. And so what happens to the rate when it's moving a lot?
It's faster
It's faster. So which way is it going to go?
that way.
That way. What color is this side?
Brown, but that doesn't make sense. It doesn't, because this is the hot part.
Okay, what if I took this out and said A plus B goes to
See.
C, okay? And this side is clear,
Did he ask to talk to you?
and this side is
I
brown,
think so.
and it's a certain color.
It's about your
If we add a ton of B, what will happen?
He hasn't seen my test.
It would
He's already marked them all.
Oh, he hasn't.
come
Oh, yeah,
clear. No,
he's
it would
going
go.
mark them to
It would
the
go
left.
this way.
And
It would go this way, and it would get browner, and it would use up all of the A, and it would all go to this side, right?
I think it's about my head did.
Because that one's clear,
My head did.
that one's clear, and it would come through and make it more brown. So you added more A, right? In this case, A is just energy. Think of energy as an actual thing in the reaction, because
Okay.
it really is. It is a thing in the reaction.
Yeah.
It's just not a physical thing. But now, this rate, the temperature's going up, this rate also increases, so we're going to draw that later and we'll show you how that works. But this rate gets affected more because it is actually one of its reactants. Like energy is its reactant. Whereas on this side, it's a product, so it doesn't affect it nearly as much.
So it's like to get so. If you add more, N2O4, it needs more energy to get up here.
If I added more N2O4, what happens when you increase the concentration of anything?
Go to 90
It increases the rate.
So if I added more N2O4, it would go this
if
way.
it's bad, I don't want you to
So
do
just
It's not bad.
so
And it
even
would
if
become
there
browner.
wasn't, even if
Yeah,
there
that's
wasn't
bad.
energy,
Yeah.
it would still be the same.
Yeah, because there's always energy in the
That's why.
system. Like
Right.
it'll be at a
Just go
temperature. You
and
add more of that,
see.
it'll shift that
I
way.
need to ask what's
It'll go
happening
browner.
at 6:30.
Okay.
No, he's not gonna tell you.
Okay.
Is that good?
Just ask him and then go. 'Cause I don't really
And I
know.
also want to ask about the reaction thing, how it goes forward and doesn't go back.
Then ask him.
How does the reaction go forward and not back?
Which reaction?
Like when you do a reaction and you said that if you have one thing.
Oh, so if both forces favor one direction,
Yeah.
that's the only direction it will go.
And it'll never return back to what it was.
If it's purely like, if it's most random on one side and it's lowest energy on that side, it's
Yeah.
really difficult to reverse that reaction. There's no equilibrium that you can reverse.
Oh, okay.
Don't open the door. It's your
And wait, and what's gonna happen to me at 6:30?
Oh, come see me, you'll find out.
Mr.
What?
Newfeld, what
Mr.
do you have to
Newfeld,
tell
I'm
me?
really
Don't open the
scared.
door.
No, I'll let them in.
Am I gonna be like suspended for being late to class?
Okay, Dylan, go. You don't need to stay here and ask silly questions.
I'm scared though.
What about?
Like, am I gonna get like infinite house jobs?
Yes.
Yeah, you should. Look at
Come.
Sophia.
Is this locked?
Okay.
Of course. One second. Let me grab the keys. I know, but I left it over here. You may come in. I will clean up very, very quickly.
Yeah. She's not like a serving one, but like that's like her title, if you know what I mean.
I actually own her.
I just love that.
No, I own her. I'm the CEO. I will.
Well, what is this?
I really do.
I don't want more challenge.
Do you see this blackness? It's from volume.
Oh, shoot. That's like not good.
What? Don't say much. You're gonna say something controversial. I just I was like, yeah, I gotta go.
Oh my god, did you see Michael?
Wait, is Michael?
Yeah.
Are you a great boss, Michael?
I did not know who
The really artsy emo one that I got a massive crush on?
Why are we so
No!
Oh, Michael, bro. I had dinner with him in Oregon. It was the best night ever. I know. He's so funny. Oh my god, he's so fucking funny. I think you should back that.
Yeah, I really should like that.
And also, Max, he died. He's so funny. He's so funny. He was so funny. Like at the beginning of the year, the beginning of the school year, he was doing just straight and all that. Like he was supposed to be. I don't think he is. Like the only people
Holding that for the hour.
no, literally.
Yes. My bad.
I don't think he is.
No, yeah.
Wait, he is?
I'm going to Germany.
I just saw his.
Who told you?
On.
Who? Are you talking about Mr.
On.
No, Michael. Michael? Yeah. Michael.
Yeah.
He is?
That's what he told me.
He told you?
Michael is so Michael.
That's the only reason it's all this stuff. Is it? Oh, you get it right? That's Facebook cop. Also.
Yeah, you're pretty, what's that?
All right, just a couple things. Welcome for coming too. I'm getting a little bit tired of reminding people about the phones thing. So everyone knows the rule.
Really sorry.
So the phones have to be in your bag, just like if you're an assembly. Okay, so